All right. So the title of this talk is Incorporating Fairness in Large-Scale Analysis System. My name is Rahul, and I'm part of the Alexa AI organization at Amazon. This work is across a bunch of people. So there are people who I directly work with. They are scientists. There are people who are engineers. There's leadership involved in this work as well because they do a lot of decision making. And we also have people from the academic world. We have professors who are well-renowned people in the field of fairness and NLP. And there's uh, it's a diverse team of people working together to do the right thing for our customers. I do want to mention that I regret that I'm not there present physically. I wish that that was not the case. But we have two talks. The second talk will be presented by my colleague Sharit on privacy, and he's there in person. I'm looking forward to the feedback to that talk as well. All right, let's move on. I'll first state the outline of my presentation. So I'll state what a typical NLU pipeline looks like for smart agents like Alexa, Google Home, Apple, or generally any sort of conversation agent. I'll sort of state the three stages. So it could be further granularized, but no, I'll just talk about three course level stages of building an energy model that includes model build, deployment, and then tracking metrics post deployment. Finally, I'll talk about some recommendations on implementing fairness in practice, and then I'll conclude the talk. So let's start with an overview of an NLP pipeline. I'm sure that there are NLP experts in the audience here, but I'll just state the typical NLP pipeline just to ground my presentation. And it might also be helpful for people who are just getting started with an NLU or who are outside the field. So in a typical NLU setting, what we do first is that there's some data collection that happens. There's some sort of model building that happens on the data that's collected. Typically, that's iterated alongside an evaluation where we make sure that the model is cooked well enough. And when I say cooked well enough, it could be across different dimensions of measurement. So some people may look at just an accuracy measure. Some people look at latency of the model when it will be deployed. People look at fairness metrics, privacy metrics. So this is a complex evaluations that can go into this offline evaluation. But once the model builder is satisfied with their model, they deploy the model, and then they track the model's performance once the deployment is done. Uh, all right. So yeah. So that's, yeah. So when it comes to data collection, there's generally some sort of data collection that happens over the data is collected from a bunch of users, or there could be offline data collection. When you're talking about fair data collection, you want to make sure that your user base is diverse. Note that this is not the only consideration in data collection. So now we are talking about generative models, where you also want to make sure that your data is ethical. So, for example, your I would argue that the model that's uh, the conversational model that's deployed outside the medical system should not give medical advice. So you want to make sure that there are data sets, there are data points where if somebody asks a conversational agent, can you tell me how to cure my fever? The response should not be a bunch of medicines, but instead it should be like, I'm not qualified to give medical advice. So there's some aspects of ethics that should be baked into the data collection. We should also properly anonymize the data, make sure that there's no personal information. So there are a lot of considerations that go into sort of building the right data set. When it comes to model build, here is a brief schematic that describes how models are built, particularly for NLU systems. We have again large sets of data. We typically build large feature models. I'm using this example of Alexa TM here, which is a 20 billion parameter model that Alexa recently released. It's a encoder decoder model, unlike the decoder only GPT models. But this is something that uh, we've been sort of using, and it's also publicly available. Uh, But yeah, once the model is built, there's some sort of distillation because these large billion parameter or multiple billion parameter models cannot be just directly deployed to production. So there's some sort of distillation that happens, and then finally there's some fine tuning on the task that's of interest. Uh, and during deployment, the same model is taken. There's an inference algorithm that's defined. That's also typically the inference algorithm that's used during the testing of the model. And then the model is deployed at various servers. And deployment at various servers is needed because your model may be serving different demographics, they may be serving different countries with different regulations. So there is a service specific deployment that sometimes happens. And finally, there's a tracking of metrics at each server to make sure that your model is behaving as expected and there's no spike in some sort of undesired behavior. So I'll talk about incorporating at about three stages. One is incorporating fairness during model build, and then I'll talk about a paper that all the work that I'll be presenting here is published. I'll keep it slightly superficial. I'll not go into a lot of results and mathematics behind the algorithm or the findings. And I invite the community to sort of look at the papers. The idea here is to just sort of tease the audience that this is what one could do in building a pipeline. I'll also talk about a fairness metric that could be used to track models performance at runtime. All right, let me start with incorporating fairness during model builds. So we have published a bunch of papers at ACL. These are typical NLP conferences. Uh, I clear ACL. Let me start with the first one where we talk about integrating some sort of devising algorithm during the model build. So in NLU, when you're building a model, one typically starts from a large model. So I gave this example of Alexa 20B model, 20 billion parameter model. We distill it to smaller models. That could be a billion parameter model or 50 million, depends upon the memory budget that you have in your deployment server. And then finally, you fine tune it for your task. So these models uh, uh, tend to be like, for example, if you're using Word, uh, it's an encoder model. A GPT model would be a decoder model. So these models are not specifically doing a task that you might be interested in. So it could be a classification task. So you may want to take that large model and then fine tune it for your production use case. Uh, so when we are looking at incorporating fairness during model building, you have to be careful about your choices in each of these three stages of model building. So let's start with a large model. When we are selecting a large model, I think we have to be careful about selecting the large model itself. We have to sort of run some tests on the large model. So this is something that we did with the 20B model, Alexa 20B model, where not only we looked at the accuracy of the model in various tasks, and we demonstrated that it was sometimes better even than the GPT-3 model uh, uh, on some certain NLP tasks. But we also, in its model card, we also evaluated several metrics on fairness. So here we give one example of fairness evaluation on Vinage Enterprise benchmark, where we were doing fairly decent. This We were second compared to this Palm 540 model. But the idea here is that in addition to having these accuracy metrics, we have these fairness and privacy metrics in the model card. We also have a carbon footprint metric. We also have a memorization metric in the paper, which I have not shown in the slides here, but I'm sure that we'll talk about it in the next privacy presentation. But the hope is, or the idea here is that whenever you're starting with a large model, we should look at the privacy, fairness, and accuracy metrics, and then make the appropriate choice based on that. Once a large model is taken, we distill it. And this is an algorithm that we published at ACL last year, where during distillation, we incorporate fairness. So the idea there was that if your teacher model is biased in certain sense, we do not instill that bias in the student model. And the idea here is as simple as depicted in the figures here. Um, so uh, the core sort of math here is we start with some sort of uh, so here during distillation, what we do is that we teach the student to emulate the teacher, and in case the teacher has bias. So, for example, here on seeing the word he, the GPT-2 model predicts profession which has doctor, surgeon, and nurse, and with these probabilities. But when we replace the pronoun he with she, it flips the professions. So what we do is that we sort of normalize the distribution by doing counterfactual replacement of he with she. We get the distribution of professions. We take an average, and this is a modified distribution that is fed to the student to be learned as opposed to the original distributions emitted by GPT. So what we saw that was that this actually had an impact on what the student model produced. So after distillation, we saw that with she, um, if you didn't distill it with the fairness objective, it would still produce nurse. But by adding this loss function, it was a little bit more fair, and more detailed numbers are indicated. Uh, so that's about distillation. During fine tuning as well, we can incorporate some fairness objectives. And I just stated one equation here, and this is the only equation, but only equation in the presentation. But it's fairly easy to understand. So in addition to having the empirical loss that you're minimizing to fine tune your model, one could add a fairness-based loss function. So here, one loss function that we tested was we not only minimize the empirical loss function, but we also track the loss between certain cohorts that contribute to your training set. And what I want to make sure is that the loss function between data coming from a certain cohort, or the loss function between various cohorts is not too distinct. So we want to minimize the loss function between the best performing cohort or the worst performing cohort in a given iteration of the model. So the idea is simple. You don't just minimize empirical loss, but also try to reduce the gap in losses between the best and worst performing cohort. And this could be easily incorporated in your model fine tuning. So this is something that could be done during fine tuning, and uh, these are some of the algorithms that we try to incorporate during model building. Now let's move towards model evaluation. Model evaluation is also it's a beast in itself because uh, we have been trying to see what sort of metrics, particularly when it comes to fairness, that we uh, uh, should sort of incorporate in gating the model. And it turns out that there are one thing that we observe that was there are a bunch of metrics when it comes to fairness evaluation, and we had to look at them very carefully. So we saw that there's a bunch of intrinsic metrics which directly evaluate the model based upon its parameters, or extrinsic metrics which evaluate the model performance based upon its performance on a certain task. And we observed that these metrics don't tend to correlate. So here's just one snapshot from the paper where we looked at the correlation between an intrinsic metric, which is heat, which is computed on uh, word embeddings equivalence in the model, and then an extrinsic metric, which is toxicity in some open language generation task. And as you can see, this plot is a bit scattered. There isn't a pattern that's emerging. So what we came to learn was that these metrics tend to be a bit uncorrelated, and you have to choose a metric by carefully looking at your end task. So if one just chooses a fairness metric that's popular, you may end up hurting yourself because you might not correlate with what your actual customers are. Now let's move towards what are some of the ways to incorporate fairness in deployment. Uh, so this is another paper that we published we presented at IEEE, which is another spoken language conference, where we just looked at how decoding algorithms in NLP would be like during generation, text generation, we would choose a decoding algorithm like top K or top P. Um, uh, I'll not go into the details of these algorithms, but yeah, you have various choices. And what we analyzed there was people generally look at some sort of quality evaluation of these decoding algorithms. They also look at diversity because they want interesting things to be generated through these models. And but we also looked at fairness. We looked at the sentiment, or there's a metric called regard. In the generations when these models are prompted with different prompts with different backgrounds, or mentioned to different backgrounds. And we saw it was again interesting to see that uh, you can get you can like people generally tend to tune for quality when they're tuning the hyperparameters of these algorithms, but there isn't sort of like a pattern there either when it comes to sort of getting the best trade-off between fairness and quality. So uh, it sort of it is a bit scattered, and you have to sort of do some sort of a grid search to make sure that you get the best trade-off between quality and fairness and diversity, and you have to choose the hyperparameters correctly. So that's another thing that we learned during the process, that you have to do a very careful tuning of the hyperparameters of your decoding algorithm if you want to hit all the 3 points that I mentioned earlier to the best of uh, um, uh, to the best of the values that are possible. So that's another thing that we learned, and that's something that we attempt to do when we are deploying an inference algorithm. We sort of do a careful hyperparameter tuning so that we get the best of the three metrics that I mentioned. Finally, I'll talk about tracking metrics post deployment. And this is another paper that we published at ACL. And the idea here, I'll try to summarize it briefly in two figures. So generally, when you have a classifier in production, there's some sort of a feature vector. So here I'm just depicting it using this four-dimensional feature vector. So say this is the feature vector on which your model makes a decision. But some of these, and yeah, and there could be an importance that could be attributed to each of these features in decision making. So given a data point and a four-dimensional feature vector, one could say, okay, these maybe the first and the second feature are really important in making the decision for that data point, but the third one is not as important. So the brightness of the color sort of depicts how important the feature was in making decision for the task. But at the same time, you can also use same feature vector to predict a predicted attribute. So you could have a separate classifier, which say, for example, predicts what, you know, just arbitrarily picking up a predicted attribute, what would be the age of the person. So it could happen that the second and the fourth feature predict the age of the person well. So what we could do is we could see if the feature that was important in decision making for the task is also important for decision making for the predicted attribute. And if you want your code classifier to not depend upon the predicted attribute, uh, you then would not want decision making based upon the second and the fourth feature. So this we sort of encapsulated into a metric where we just sort of multiply these two vectors and can sum it up to understand whether your classifier is making decisions based upon features that correlate with predicted attributes. And if that tends to be high, we can sort of take remedial actions to reduce the dependence on of your classifier on predicted attributes. We also showed that this metric is correlated um, uh, with with theoretical definitions of fairness, such as group parity and individual fairness. But I'll skip that for the sake of this presentation. Finally, I'll talk about some recommendations on implementing fairness impact practice. So, a few things that we take care of when we are sort of incorporating fairness into model building is, it, writing them into papers is one thing, but putting them into practice uh, takes more care. And I'd like to thank the engineering team that worked with us for this. So what we want to make sure is that when you're building an algorithm for fairness, uh, we incorporate the algorithms into the core model building packages. Because otherwise, if you don't offer these as entries into the YAML file or the JSON file, it's easy to have these algorithms, as sort of like as sidekicks and not be part of the main model building recipe. So we want to make sure that these algorithms are part of the core model building package. Similarly, when we build mechanisms, track fairness, uh, 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 we want to build mechanisms to track fairness post deployment, and they have to be incorporated in the core metrics that are tracked, such as latency or customer satisfaction if it's tracked in some manner. Finally, we also establish a feedback mechanism from what we see in the real world versus uh, 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 we build a feedback mechanism between what we see in the real world to what we sort of build. We sort of want to draw learnings from what we see in the real world and sort of incorporate it in the next cycle of the model build. And also, it happens that things change at a fast pace. So sometimes you may want to sacrifice um, incorporation into the core model building packages. But if you do that, the recommendation is that there should be a fast follow up to also incorporate novel improvements or new algorithms into your core model building packages, in case it's not possible to do it in the first shot. Summarize somewhat into these figures. I'll sort of rush through these given the time. But yeah, the idea is that once during model building, you incorporate sort of the core algorithm into the model building packages. Same for offline evaluation, you have the fairness metrics alongside the core metrics. During deployment, you not only have accuracy related gates, but also fairness related gates, which are part of the core packages. When you're tracking the model's performance, you should track it based upon certain fairness metrics. So here, for example, we can segment our customers and then look for performance gaps and explanations for them. We should track the fairness in standard accuracy or track fairness metrics in the standard accuracy dashboards, and then draw a feedback loop between what we see in the real world to the next cycle of model building. So one simple way is like, if you see that you're not performing well on a certain customer group, uh, there could be some sort of active learning. These are simple techniques, some sort of synthetic data generation that could be used in the next round of data collection, so that the next model that's being built is strong on that demographic. Yeah, so that I'll like to conclude my talk. So I hope I made my case clear. I presented an overview of typical NLU pipeline and talked about incorporating fairness at three different stages. The model build, where I talked about starting with a large model, distilling it and fine tuning it. Incorporating fairness in deployment, where I talked about carefully fine tuning hyperparameters of decoding algorithms that are used typically in large language models. Tracking fairness using a metric that we came up with. Uh, um, uh, and then finally, I presented some recommendations on sort of having these algorithms be tightly knit to the regular model building process. With that, I would conclude the talk. I'll click on my video. I'm happy to answer any questions.
Thank you very much.